And please.
Okay. Okay, thank you for the opportunities for presenting our research results here today. And my name is Yuta Notsu, as introduced, and I'm in LASP in the NSO, in the partially affiliated with some Japanese institutions also. And today I talk about the recent observations of stellar flares. It's becoming a very hot topic in our field, and also discussing possible mass ejections, including a lot of plasma physics, of course, and collaborated with these people. And before going into detail, this is just my introduction. So as introduced, I got PC in 2019, and working with Professor Kazunari Shibata there, and, in the solar physics group there. And after that, I came here, and I mainly work in the East Campus in LASP and NSO building. And our recent studies, the observational studies of stellar flare activities based on solar knowledge. And mainly I'm doing statistical properties of stellar flares on solar type stars. And also recently, much more interesting spectroscopy observations to detect stellar coronal mass ejection. So I explain more in detail later. So before going into detail, I start my talk on a brief introduction of solar flares. Maybe you heard about solar flares, right? And yeah, as you may know, large solar flares are large eruptive events in the solar atmosphere, and this is both sudden magnetic energy release, especially caused by magnetic reconnection in the solar corona, and observed in all wavelengths. So, for example, this is a image of soft X-ray image of the sun. As you can see, there are a lot of explosions on the surface of the sun. And also, this is a Hinode satellite movie of a solar flare. And the sudden between sunspots, sudden, yes, it's real occurred. And this is a very famous, popular flare in solar physics. And as like this, there are a lot of various emissions, and the time scales are from 1 minute to 1 hour. And as I already explained, the solar flare occurs a magnetic reconnection in the corona, and then magnetic energy is transported to the lower atmosphere through high energy particle acceleration and also thermal conduction. And then lower atmosphere is much more dense, so the energy is deposited to the lower atmosphere. Then a lot of heating occurs, and some plasma is evaporated into the roof, and then this kind of roof structure is observed in X-ray. And also, this is a movement to the bottom, but in addition, plasma is also ejected from the sun, associated with flare. This is called mass ejection or coronal mass ejection. So we say CME, coronal mass ejection, CME. And the solar flare itself is very interesting from plasma physics point of view, but from a space weather aspect, extreme events or extreme solar flares are very important because in recent years, because large solar flares can have a severe impact on our Earth and the society, as you may know. So if coronal mass ejection caused by solar flare occurs, this plasma propagates into the interplanetary space and disturbance on the magnetosphere, of course. And this can affect very much to the Earth. So this is a stereo satellite image, not satellite, stereo spacecraft image, both imaging both Earth and Earth. And one of the biggest solar flare recently affecting severe damage, for example, in transfer system, electric system like this. And one of the largest solar flare or solar extreme event is the Carrington event, occurred 1859. And this is actually the first solar flare we recorded in a modern way. But this is also the largest flare we recorded because there are a lot of magnetosphere observation already. And this is one of the largest magnetic storms in our history. And this is a sketch observation at the moment, but after that, there are a lot of auroras and also telegraph disturbance already. And several large-scale events have been detected in recent, similar large-scale events have been detected in recent 100 to 200 years. But there are a big question: do larger players come or sun or not?
Do you happen to know how long it took people to connect this activity with the sun? Did they know right away that this weird telegraph behavior was connected with activity in the sun?
I'm not sure the people at that moment realized that, but there are a lot of problems with reports, and recently some researchers coming back to the record and oh, this is caused by solar flares, I think. And yeah, but that effect was as far as I know, that effect was worldwide. There are a lot of papers actually.
Is the picture on the lower right, is that like an animation of the aurora, or what is that?
Oh, sorry, I have to explain. This is sunspot.
Oh, sunspot.
Sunspot, okay. This is a brightness increase in optical light.
Okay.
And not only one people, but two observers independently detected the same flare.
Okay.
Because they sketched sunspot size already from 60th century, 70th century. From 400 years ago, from Galileo started. Okay. And now, solar flare observation, modern solar flare observation has a history of 160 years now. So then we know occurrence frequency distribution of solar flares. So then, we know frequency distribution of solar flares for very wide range. This figure, vertical axis is the flare frequency, and the horizontal axis is the flare energy of each event. And there are several measurements. But simply speaking, there is a power relation like this over very wide ranges. In the largest flare is energy similar to Carrington event, so around 10 to 32 is the total energy radiated from the flare. And the frequency is once in 10 to 100 years.
I'm just not sure I understand the units on the vertical axis, erg inverse, year inverse. I can certainly understand a frequency per year, but how does that inverse erg enter into the calculation?
If we integrate, we can also plot the power frequency also. And we can convert easily to once. Sorry, I showed before that. We can plot once like this. But we don't know only with so flares larger than this is once if there are once every 1,000 years or 10,000 years. But modern solar observation is only 160 years, so we don't know only with modern solar observation for this area. So possibly there is a cutoff here, but we don't know how we can extend or not. But if we look at the other star, not the sun, other star, since I think 50 years ago, there are some observations of a much bigger flares on other stars. It's called superflare. Have you observed on variety of stars? So, for example, this is an observation of the X-ray observation of the very young star. There are sudden brightness in X-ray, and we can convert the energy, and then this flare at least 10, from 10 to 10 to the 6 times larger than the largest solar flare. It's called superflare. But the stars having superflares were very different from the sun. So binary stars are very rapidly rotating stars because so it's very young, rapidly rotating star. Because the young star was born with very rapid rotation, but because of the solar wind, the star lose angular momentum gradually. So the stellar rotational period or rotational velocity gradually spin down to the solar age. So if star is rapidly rotating or cool, very cool, and having stick convection zone, can have a more efficient dynamo mechanism. So if, for example, if stellar rotation velocity is very high, it can generate magnetic field more efficiently. So then this is very different from the sun. So then it has been believed superflares do not occur on slowly rotating sunlight because the sun is very slowly rotating now. So maybe people believe dynamo mechanism is not so efficient. So people believe like this.
Do these stars or some of them have a similar mass to the
Yes,
sun? Okay, so
similar
they're not-
mass, but very young. But we asked the question: is this really? So then there is a good data. There were good data sets. So we use the Kepler space telescope data. Kepler is originally designed for exoplanet search. So this satellite, this spacecraft observed the one area of the sky continuously for 4 years. It was to search for exoplanet. If exoplanet exists and passing through the surface of the star, the stellar brightness becomes fainter. So trying to detect such exoplanet trigger the modulation. This satellite observed many stars in one region for 4 years. But this is very good for flare search. So monitoring for stars, many large number of stars for longer years. And if we can observe the sun for 10,000 years, we may detect one superflare. Because if we can observe the sun for 10,000 years, we can detect one data point, but it's not possible because we only have 100-year history. But if we can observe 10,000 sun for 1 year, then it statistically corresponding to the observing one sun for 10,000 years. So this is our method. So then Kepler is a good sensitivity also. So Kepler can detect superflares on sunlight, but actually capability to detect superflares on sunlight. Actually, this is observation of the optical light. Solar flares are very active in X-ray, but in optical light, the brightness change is very faint. So in the case of the very active solar flare, usual solar flare, amplitude is just around 0.3%. Yeah.
Sorry, just before you.
0.3% or like that. Okay.
Do people use X-ray telescopes to look for these flares?
Recently, yes, but X-ray survey telescope is not good for
Long exposure, right?
yeah. X-ray telescope is more expensive and it's very difficult to survey. So time cadence is bad. So for now, Kepler was the best satellite. Of course, we can do this in the future. And using Kepler space telescope data, we discovered many superflare events on variety of solar types. Solar types have a G-type in sequence, same mass with the sun as the sun. So we discovered many superflares. So this is an example light curve of Kepler superflare data. So the stellar brightness is still moderate. Like this, I explain in the next few pages. But there are sudden brightening increase here, possibly here, and here. And if you zoom out, the amplitude changes like this. So relatively sudden brightening and gradual decrease. This corresponds to flare, light curve. And this amplitude is different, but this is an example of that solar flare also. So using more than 10,000 solar mass stars data, we discovered many superflares. And considering the amplitude difference, this corresponding to much larger flare compared to usual solar flare. So this corresponds to superflares. The energy is at least 10 to larger than at least 10 times larger than the largest solar flare. Okay. Oh yeah.
So on that plot, wouldn't that be showing multiple silver flares over the course of like a month right there?
Yes.
So that's a lot more frequent than 1 in 10,000 years.
Yes.
And this is one star, right?
Yeah, actually, this star is a bit younger than the sun.
Okay.
So rotation period is I think that our 10 days, and also some stars showing multiple flares. So this is a very interesting point. Some stars showing multiple flares, but in different ways showing no super flares. So possibly the activity changes or not.
And then, so you have a note at the bottom, but can you explain how we derive the energy? Is it extrapolated from the change in optical emission?
Yeah. We are actually optical emission is basically
Actually, maybe I should back up. Where is most of the energy emitted in, like, is
yeah, this is always
X-ray
interesting.
relative to optical?
Actually, recent high resolution solar flare observation suggested that dominant energy is from optical. X-ray amplitude is very large, but the total energy, optical energy is the dominant part. Of course, we have to study energy balance of plasma ejections and the flare emission, but for flare emission, optical is the dominant part for most of the flares.
I see. So the small change in brightness is just because the rest of the
Yes.
star is
Yeah.
in optical.
Yes, because background is already blind.
Right.
Okay, now we have found a very large number of flares. So then, but we have found many events, so we can discuss more physics. Not just discovery, but also we can discuss physics. So let's discuss the physics point of view more. So then first, what's the necessary conditions of large flares? In the case of solar flares, there are some studies. So this is a plot of many solar flares, not super flare of the star, solar flare on our sun. And the vertical axis is the peak soft X-ray flux, so it's the size of the flare. The size of the flare, and the horizontal axis is the sunspot size. Then there are some correlation, and also the color. So first, if please see the upper limit first. If large sunspot magnetic area, then flare energy, upper limit of flare energy is larger. Of course, we have smaller flare, maybe. So large sunspot can be a necessary condition of large flares. And also, there are some color change in some types. And this type corresponding to the complexity of sunspots. And the alpha type, beta type, delta type. So delta type is the more complex. So complex of magnetic polarity, easy to trigger magnetic reconnections and the driving of the coronal mass ejection also. But this is also interesting topic of solar physics. Anyway, large sunspot, at least large sunspot, the necessary condition for generating a large solar flare, relative large solar flare. So if there are large sunspots on the sun, then we have to consider the possibility of large space weather event. For example,
What are the units on the for spot size? Are those kilometers or?
million solar hemisphere. So this is 1% of the solar hemisphere. So 1%, 0.1%, 0.01%. Yes, 1%, 10%, 100% of solar hemisphere. Now, of course, we can convert to the kilometers physical size. Oh, yeah. And so then, can we apply this view to the superflares? And the answer is yes. So let's see again Kepler space tensor data. So if we already see this light curve, so there are a lot of superflares, but there is also modulation. And many superflare stars show quasi-periodic brightness modulations, roughly periodic modulation. When these modulations are after a lot of investigation, these modulations can be explained by rotation of a star with large star spots. So if there is a very big sunspot, star spots located on the surface of the star, if the star spot is on our side, star brightness becomes fainter. On the other side, the star brightness becomes brighter. So then, the amplitude corresponding to the starspot or sunspot coverage, and the period corresponding to rotation period. And the amplitude is much larger than the sunspot amplitude. Sunspot also showing the duration on the sun, but the amplitude is very small. But in the case of the star, amplitude is very larger. So then we can have a view of this kind of superflares with severe large starspot. And this view is also confirmed with a different way, not only light, but also some spectroscopic measurement. I skipped this part, but there are some evidence of this. And we can compare with flare energy point of view, also for same thing. So in this figure, flare energy as a function of the sunspot size spot group area. So actually, this is almost same figure with this. So flare size and spot size for superflare event and usual solar flare. As you can see, superflare data point located on the right side. So larger spot. So this means the larger spot. And there can be a rough scaling with calculating magnetic energy that can be stored around the sunspot area, starspot area. And roughly speaking, very roughly speaking, such starspot energy can explain magnetic energy stored around the starspot can explain flare energy. Now, of course, the stellar data have some ambiguity because this is only based on amplitude modulation. So if we observe the star with different viewing angle, amplitude can be underestimated. So the data points can locate on the left side. So in reality, I think the data points locate a bit right side. But anyway, there are rough scaling can be possible. So large magnetic energies are needed for generating large superflares. So this is the energy point of view. And also, initially I explained the younger star have a much more superflares, very active superflares. It's believed in the past. And this point of view is investigated more in detail with Kepler data because we have found many events. So then we can discuss how superflare activity, how flare activity changes from young sun to current sun, young rapidly rotating sun to current sun. So these two plots showing this. So this left figure showing flare energy, superflare energy, observed with Kepler as a function of rotation period. The sun is rotating with 25 days, around 1 month. So the sun should locate around here. And so lower limit is affected from some observation bias, but please see the upper limit. So upper limit of superflare energy still depend on rotation period. So the sun have a superflare, the sun similar to star similar to the sun. The sun possibly generates superflare up to 10 to 30 The largest solar flare we know in recent 160 years is around here. So possibly 100 times larger superflare occur on the sun-like star. But the young sun rotating around with rotation period of 1 day, 2 days, up to 10 to 36 cells. So 10,000 times larger superflare can occur on young rapidly rotating. And also frequency also can be plotted. The young star have a higher frequency, and the lower stars, slowly rotating star have a smaller frequency. So anyway, flare activity depends on stellar age. So very young stars have very actively rotating and rapidly rotating, and a lot of star spots and showing more frequent, more energetic superflares. While even sun-like slowly rotating stars still have superflares with 10 to 34, 100 times larger than large superflares. Then let's go back to this plot. So I already explained flare frequency is explained with power distribution. We want to know this area, how frequently is superflare on our sun. And then we can plot similar plots based on Kepler data. So this is a flare frequency distribution frequency distribution, same vertical axis as a function of free energy from Kepler data for several rotational period ranges. And the sun is included in this region and this group because the sun is rotating with 25 rotation period days. And the youngest have a higher upper limit of the energy and also higher frequency on average. And then we can combine these two figures like this. So these are solar probes and increasing years, but these red points are in the latest analysis result of superflare frequency on our sunlight cells. So then we can say there is a one power, roughly speaking, there is a one power relation. And the superflares whose energy around 700, whose energy is around 10 to 34 for 1,000 times, no, 100 times larger than the largest solar flare, 100 times, can occur on sunlight cells once every 3,000 and 6,000 years, respectively. And so possibly a bit smaller flares also occur at a higher frequency. So this is a good, one of the interesting views of the superflare frequency from Kepler data.
Can you remind me what we think the Carrington flare energy was?
There are some discussion around, but several factor times 2-3 times per 10 to 12. Okay. Okay, this is a mid summary. I have a CME topic, but this is a mid summary. So Kepler and I don't explain this data, but I explain the next slide. So at least flare activity depends on stellar age. So younger rapidly rotating stars have a more frequent, more energetic flares, while even some like slowly rotating stars, you have a superflare with 10 to 34 once every 1,000 years. So and then superflare have a energy from these strong magnetic field, large starspots are necessary. And also, I explained the stars similar to the solar mass, but flares also in a similar different temperature is also investigated. And this topic is I skipped that point because the time is limited. But this point is also becoming interesting for understanding of the other exoplanet system recently. But okay. Now, if you have any questions, please.
Yeah, just I'm curious, are there any signatures, I don't know, geological, maybe tree rings, ice cores that on Earth that go far back?
Yes, I explained this, right?
Yeah, okay.
This is becoming a very interesting topic, honestly. Now, we have a stellar frequency, but as you ask, people can, and we have a question. Are there any records on our Earth? The answer is possibly true. So now people are studying long-term data on the Earth related with solar phenomena, especially radioisotope measurement, carbon-14 in tree rings and also beryllium-10 in ice core. And this is one of the example of 1 year time resolution light scan, not light scan, in 1 year time measurement results of the carbon-14 amount. And some long-term changes caused by long-term solar activity. But there are sudden sudden increase of carbon-14 amount. Carbon-14 is a radioisotope, so carbon-12 is a general one. But so sudden increase, and like this. This can be caused by the strong cosmic ray increase on the Earth, on the surface of the Earth. Some cosmic ray increase from the sun or for distant some astronomical source like gamma ray burst supernovae. And that event was first. This event was first discovered just after our superflare discovery in 2012. But some people, there are some discussions, supernova or solar results, but now, after that, people are invested more in detail. Same event are detected in Earth core. So very important. So not only carbon-14, but very important. At the same time, some peak occurs. So this is not error. So some worldwide event. And not only one tree, but many trees in Asia and Europe, both showing and more than 10 trees showing same increase, and also same increase in Earth core. So it's a worldwide event. And also not only one event. Now, in recent 10,000 years, only 1,000-year data is investigated, but at least 8 events are detected. And the recent solar flare doesn't show this large amplitudes, maybe like this. So this can correspond to events at least larger than Carrington event. And also this is their event. So now this is become, oh yeah.
But as you said, isn't it still an open question whether it's solar activity or other astrophysical origin?
Some people still discussing, but as far as I know, many people are now, I think 5 years ago, there are still discussions, but now 8 events detected. And if, for example, caused by supernova, there should be some supernova remnant, at least 8 supernova remnant, but nearby, there are no remnants.
Statistical argument.
Yeah, and also gamma ray bursts, I think statistically, it's almost rejected.
Right. So if it was 2, you could say one of them was supernova, one of them was the gamma ray burst.
Yeah.
On 8, you can't say.
For example, there are no recording of the supernova here and here.
I see.
And it's not possible. Gamma ray burst is a much more rare event. So then the solar event is a more possible explanation for this event. But how, so possibly events can larger than Carrington occur once, at least 8 events in recent 10,000 years. But how can we compare with Superflare observations? So our observation is rare. The brightness increase on the surface of the star, but these measurements are on the Earth, and there are some gaps. So there's coronal mass ejection occurred, and in the coronal mass ejections, particle is accelerated in a shocks or in a plasma, and then particle is penetrated into the Earth, and then carbon-14 amount will increase. And
So actually, can you describe like exactly what the process is in carbon-14? Like what particle comes in to affect it?
proton.
A proton, a high energy proton?
Yes. Yes, high energy proton can trigger, I forgot the exact reactions, but it can trigger some chemical reactions.
And do you know the energy range of the proton that we're talking about?
Yes, 100, several hundred, maybe or like that. And actually, barium-10 carbon-14. I can show you the paper later. But these I forgot the exact number. But these 2 measurements show is sensitive to the different energy ranges. So there might be some particle spectra is also can constrain. Must still have an open discussion now. Anyway, we are collaborating in an interdisciplinary team in the International Space Science Institute. We have a meeting in June this year. So from stellar side and also solar, also radioisotope observation, trying to cooperate to this problem. And also recently there is a good review paper on this topic. But the problem from our side, we have a flare observation, but no particle observation on the star because it's very difficult. But flares and particles, they are still large scatter, even in the case of the solar flare. So this is a flare energy in flare graph, flare size versus particle strength measured on the Earth, recent Earth. And possibly such carbon-14 events located around here, but it's difficult. So we have a flare frequency distribution around here, but there is a large scatter. So we want to constrain. So then we have to go step by step. So we have a flare, superflare observation here, but we don't know how does coronal mass ejection occur. So this is a topic should be investigated. So now we have flare, as I explained in introduction. Flare is caused by magnetic reconnection here. The energy is injected in corona and energy transported in lower atmosphere. And we observe the emission from here. But plasma is ejected also. But so the observation constraint of stellar coronal mass ejection is very important to understand particle intensity on their Earth. Also, so how large? But also, from other point of view, stellar coronal mass ejection observation is important. So the previous topic was mainly about the possibility of superflares and also super CMEs on our sun. But recently, possibly more interestingly, I don't know, younger superflares on younger sun is also becoming interesting. Because as I presented, youngsters have a rapid rotation, so flare frequency is higher. Younger stars showing a high magnetic activity. But now people are discussing how our planet evolved, triggered by a recent finding of a lot of exoplanet system. Now we can investigate the youngster with some planets. And planetary formation or planetary atmosphere evolution, and some theoretical studies suggest that some planetary atmosphere is strongly affected from stellar activity, especially a lot of high energy particles caused by superflares, for example, and a strong UV emission from superflares can generate a lot of chemical reaction and also atmospheric loss. Such solar flare and chemical reactions are also observed recently now on the observation of Mars. But this topic is becoming very interesting. Now, for example, one theoretical paper in Nature Geoscience suggests the higher frequency of superflares on our on the young sun has large effects on atmospheric warming and prebiotic chemistry, especially prebiotic chemistry, because a strong UV from superflares and also strong particle events from accelerated particle can trigger some chemical reactions necessary for understanding the atmosphere on our current Earth. So then particles and so coronal mass ejection is very important to understand this topic.
Sorry, can you remind me what SEP is?
Solar energetic particle or stellar energetic particle. Yeah, sorry, I love the terminology. And CME is a coronal mass ejection. So now, stellar CME observation is very important. And now, recently, we detected several, for this paper one, possible detection of stellar coronal mass ejection associated with the superflares. So this was published in Nature Astronomy last December, and we have the press release also see border. I explain. So we previous observation used the Kepler space telescope measuring stellar brightness, and we have a newer type of Kepler. Kepler already ended our observation, but recently TESS satellite is a successful mission of Kepler is launched and observing the stellar brightness in a similar way. So, but we additionally using a ground-based telescope simultaneously observing the same star. And TESS observing the stellar brightness with very high time cadence, but this observes the H-alpha spectroscopy, so observing a spectroscopy line to measure Doppler shifts of the intensity of the star, especially from the chromosphere, plasma ejection component. And we are observing a very active young superflare because this star is very young and showing superflares very frequently. So showing superflares once in 10 days. And we observed one star in total for 32 nights, collaborating with the Japanese collaborators because their telescope is located in Japan. But we observed one star for 1 month. And then we detected several events. And I show the example. So this is a TESS light curve similar to Kepler. So the brightness increase with flare. So this is superflare. But in H alpha, this is a chromospheric line intensity. Flare occurs here, also in H alpha. It's as expected. And it's usually observed on 1 hour sun. But after the superflare, there are some brightness decrease decrease after flare. This corresponding to a post-flare H alpha dimming is observed. This can correspond to cool material appear just after the energy release phase. So after flare, some cool plasma ejecting absorbs the stellar light. And actually, this component can explain the plasma, if plasma is ejected. In the case of H alpha, this is observed in absorption in the sun. And actually, this is a difference profile, different from a pre-flare phase. So in a flare, H alpha intensity increases with the no Doppler shift. But during this dimming phase, absorption is shifted to blue part. Blue means this component is moving further. So this can be explained with this view. So flare emission is first observed here on the surface of the star. And if the plasma is ejected, this can absorb the light from the star because of considering the density, the temperature difference. This can absorb the H alpha intensity, and also it's blue shifted. So then blue shifted absorption is observed. So this can be a first detection of possible coronal mass ejection on solar telescopes. Oh yeah.
So just making sure I'm following. So in the middle panel there, the red and the blue curves are different. No, I was about to say something. No. What? Can you clarify what the two different curves are? I see that the blue is supposed to be the blue shift absorption. Mm-hmm. What is the red interpreted as?
Red is H alpha line at the flare peak.
And the blue is not, is blue shifted H alpha?
Yeah.
Actually, the blue is at a different time.
Different time. So this component already disappeared.
I see. So thank you.
Yeah. And so this can be caused by this blue shifted absorption. And this line profile is very similar to the very smaller solar counterpart. In the case of the sun, similar H alpha line profile is observed. So we use the solar data also. This is a zoomed up, very much smaller solar counterpart. But if flare occurs and mass is ejected in H alpha, similar line profile is observed. So of course the sensitivity is much different because the sun is very bright. But the line profile changes also time difference very similar. So then using the absorption and also the amplitude is very different, because stellar event is much bigger. We integrate, convert to the standard star measurement. So the intensity is very, amplitude is very small, much larger. And using this line profile intensity, we can estimate how large amount of mass is ejected. So then we can discuss how large amount of mass is ejected. So this figure is the ejected mass based on Doppler shift measurement or also solar observation as a function of flare energy. And in the case of the solar flare, there are a lot of huge amount of coronal mass ejection on our solar associated with solar flares. And how large amount of mass is ejected But this is just an understanding. Our superflare data points can locate here. So at least the mass 10 times greater than the largest solar mass ejection occurred associated flare larger than 50 times larger than the largest solar flare. So then indicate young planet system around young sun can be more severely affected with ejection than solar case. And also, roughly speaking, now we have to investigate more and more events, but we may extend the scaling to the large energy part. Of course, we need more stellar events. So our stellar eclipse observed. So our stellar event can be a proxy for possible coronal mass ejections on the young sun. So this could be related to evaluating the effect of planets, especially on young age, and also possibly a proxy for understanding superflares on our current sun. This is the first step to estimate particle strength, energetic particle strength to trigger carbon 14 increase. But this is step by step, so very long way. And also, mass ejected from the superflare is very large. So some people discussing stellar CMEs can affect the evolutionary history of stellar mass and angular momentum loss. And some people, because the sun is losing some mass to some amount, but more statistical investigation needed. And also, I don't go into detail, but in future, more observational attempts are needed because we only detect the blue shifted amount estimation, but there are some other possible measurements using other wavelengths, the X-ray, for example, and also discussing how big superflare coronal mass ejection is ejected to trying to compare with some surface modeling of magnetic field. So future studies are very important. So the time is almost approaching. So this is the summary. So in the earlier part, I introduced mainly statistical studies from Kepler of data. And the flare activity depends on stellar age. The young stars showing superflares, more frequent and more energetic flares. But even sunlight stars possibly showing superflares up to 10 to the 34, so 100 times larger than the solar flare. Recently, there are some candidates of possible mass ejection from the star. So this can be a start point to understand a much bigger picture of a big plasma ejection event on the surface of the star. So that's all for now. Thank you.
Thank you. Thank you very much for a very interesting talk. So now questions from here or online?
Yeah, that was awesome. Thank you. You touched on this, and maybe you said it, but I missed it. You're talking about in the previous slide, just effects on exoplanets. Are there is there any chance that you would actually have an observational signature of something in the spectrum of the exoplanet's atmosphere that's actually changed because of the?
Oh yeah.
Do you think that we can see a difference?
That's an interesting point, and
or is it more just, we know that it has some effect on Earth that we can see by looking back at ice cores, and therefore yours?
Yeah, of course, the work on the Earth is an interesting point, but there is some system, not Earth Mars planet, but there are some systems. Recently, some observations of the exoplanets showing atmosphere loss.
Atmosphere goes.
Lost.
Lost.
Is losing. Atmosphere is being lost, and host is very active. And for example, hydrogen lime alpha observation or X-ray observation showing if atmosphere is lost, there are some observations in there are some discussion in the cause. But if, for example, steam occurred and the increase of the atmosphere loss, for example, for Jupiter-sized planet, Earth is very small, so it's bigger. But the Jupiter, very big Jupiter-sized planet, exoplanet, it could be possible. There are some discussions actually. Thanks. Any other questions also from online?
So I have a question. Is the duration of superflares much larger than normal solar flares as well? Does it
Yes.
scale with size?
Yes, I skipped that point, but I skipped that point, but there is also discussion in our recent papers. So we plot several flares from the sun to superflares in various years. And the flare energy and the flare duration, roughly speaking, larger flares have a lot longer duration. So maybe it takes time because the scale is become larger. So it takes time to eject all energies. So yeah, this is also interesting point actually.
And sort of related to this, you probably said this and showed this, but I didn't quite get it. Are super flares and normal size flares, do we believe they're connected, just the same thing on a power law? Or are they, do you think they're distinct
Not
mechanisms?
at least based on current observational data, not distinct. Of course, some gap for size, but frequency, also durations and energies point of view, only the size, event scale becomes larger, but easily understand with same physical mechanism. But important point is how to generate such large magnetic energy. That point should be investigated to understand why, whether the sun generates superflares or not.
Is there a flare size that, like a critical flare size that we would be concerned with on Earth, like in terms of energy, on your energy scale?
Oh, actually, even current event is very dangerous.
Yeah.
Because we have a lot of spacecraft, satellites, and also we going to the moon, Mars. Yeah, space X satellite with failed because of recent small scale solar flares.
The energy grid would go down, right?
Yeah, energy grid down.
Yeah, lots of more power lines.
Yeah.
Actually, it's. I mean, is it the case that sort of the maximum common solar flares that we observe are just a little bit below that threshold? I mean, have we just gotten very lucky?
I remember
yeah.
reading about this in the plasma 2020 report.
Yeah.
The answer is in there. I forget what it is.
Yeah, and I heard that 2012 flares similar to current size occurs on our sun, but this occurs on the other side of the sun. Then no effect on the Earth. So
That was sort of my question. I know that the Carrington currently was as bad as it was, not just because of the magnitude of the flare, but because the solar longitude where it happened was exactly wrong for where Earth was. And I'm just curious in terms of, for a flare of that magnitude, what is the probability that we're going to get whacked by, very unfortunate alignment? And as the flares get bigger and bigger, are they also larger in size, and therefore, the probability that we'll suffer the consequences goes up with the magnitude of the flare?
That's right. Yes. So the location of the flare site is very also important. Yeah.
Then corresponding, can we observe flares on other parts of the sun and CMEs that would be dangerous? Like, can we increase our statistics that way?
Yeah, now some satellites, for example, in the solar orbit or stereos. So, for example, I showed that image, but this was observed, not from us, of course, from the different point of view. So there are some spacecraft now observing, and for example, in Mars, if people send humans to Mars, it's dangerous. If the Earth is located on the other side.
In the first half of the talk, you talked about sort of trends in rotation rate and solar flares. What about binary versus isolated stars? Like, do we have an idea for whether that makes a difference on the frequency of solar flares?
Yeah, binary is showing more frequent and larger flare. because that can trigger more efficient dynamo mechanism. In the ice skip, but for Kepler cells, for many bright Kepler cells, we conducted more investigations whether these are the binary or not. And there are no signs of binary. Then we can use this. Using a spectroscopy observations, we also discussed this point. So, any questions?
I have one more.
Okay.
Can you say what is special about tree rings and ice? I assume like deep Antarctic ice or something that allows you to see evidence. Yeah, like could we find some sort of radioisotope that might give us evidence of past solar superflares in, say, some rock somewhere, or what's why tree rings and ice?
Why tree? One point is I think tree rings ice core time resolution is good because tree rings for every year, and ice core is same. So there are seasonal change. So ice core is also not tree ice ring. I don't know the name, but every year or 10 years. So there are seasonal evidence. And for example, some studies trying to use moon rocks to estimate the possible solar activity related particle amount, but this only is detection of the accumulation of the previous event, integration. But tree rings ice core can be used for better time resolution. So that's the point I think you. And originally this was started for understanding global warming and climate change, because the climate is changed, tree rings amount changed also. Any other questions?
There are no more questions. Let's thank you again.
It's really cool.
Thank you.
Thanks.